Alright, so here we have a problem. We've got a block. It has mass m. We release it from rest at the top of this ramp. The ramp is at an angle theta. And this initial part of the ramp, or the top part of the ramp, has no friction at all. And then the lower part where we're shaded right here does have friction. So I release it from rest. It slides down for a little bit. Then at time that I'm calling TF, the block hits this friction part and it starts slowing down and comes to a stop right there. Now in this problem, I'm going to give you the coefficients of kinetic and static friction. What I want you to do is find the time it takes for the block to come to a complete stop. Now this is one of these classical dynamics problems where you have to compute something. And for my students, I prescribe a process. I call it the problem-solving process, which has very specific steps. If you go through the steps, if you can execute all the steps, I would say it greatly increases your chances of success. So the very first step of this problem-solving process is to list the things in the problem that are given to you, things that you can assume you know. So it's telling you that there's a mass m, for example. So that goes on my list. M is on my list. The angle of the ramp, that's also on my list, the theta. The time at which the block enters this region of friction, I call that TF. That was on my list of things. Mu k and mu s, those coefficients of kinetic and static friction, these are all given to us. And there's one more thing you can probably guess we need to be known. That is something about gravity, right? Gravity's pulling this thing down. Gravity's driving the system. It doesn't explicitly list gravity here, the acceleration due to gravity, but that is a given too. G is always a given. So in my class, you can leave that G off if you want, or you can put it on there. Either way, that G is always given. So there's one of the steps on my checklist. I want you to list everything that's given to you. And also I want you to list explicitly, list it out, don't just keep it in your head. I want you to list the thing that you're supposed to find in this problem. So what we're supposed to find is what I'm calling the stopping time. And I'll give that the name TS. So TS is my stopping time. So given all this stuff, find the stopping time. Now the next step in this process is to draw the free body diagram. So let me start it right here. So here's my block, and so what I have to do is draw the forces acting on the block, right? So we've got a force down. That's the force due to the weight. So I'll label that W, at least for now. And then I've got a force acting this way. There's the normal force. This is the force that keeps the block from penetrating the ramp. I'll call that N for now. And let's see, when the block is just sliding on this first part, that's it. When we get onto the friction part of the slope, this rough part, if you will, then we're also going to have a friction force too. So I can draw that as a completely separate free body diagram with these two forces and the friction force, but I'm just going to put it in right here, right now. So there's the friction force. I'll just call it F right now, and I'll talk more about that in just a moment. Okay, so there's all my forces on my body, and I think we're ready to move on. So I'll state it more thoroughly in just a moment, but we're going to be applying Newton's second law. So in other words, we're going to sum up all our forces, and we're going to set that equal to mass times the acceleration of the block. Okay, force, those are all my forces. Weight, these are things pushing and pulling on the object. And then that has to equal mass times acceleration. So I need also what I call a mass acceleration diagram. Sometimes it's called an inertial response diagram, but a mass acceleration diagram has a nice little abbreviation, MAD, I kind of like, so I'll keep it mass acceleration diagram. Okay, so I have the block drawn here for the mass acceleration diagram, and what I'd like you to do before we continue on the video, what I'd like you to do is draw what vectors go on here, okay? Pause the video right now and try it out, and then restart it once you have something. Alright, so here's what I'm going to do for my mass acceleration diagram. I'm going to have a vector that's pointed this way, and I'm going to label that MA, just like that. And that's it. Okay? First of all, why is it in this direction? Well, remember this block is just moving along a straight line. So if I have an object moving along a straight line, then its acceleration has to be along that line. It could be in the direction of motion, it can be in the exact opposite direction of motion, but it has to be along that line. Now, there's a tendency for students, at least at this stage, and it's an understandable one, I think, to want to put somewhere on this mass acceleration diagram maybe a G or something like that. something with g, the acceleration due to gravity, that thing right there. And this thing has units of acceleration, right? It's 32.2 feet per second squared, or 9.81 meters per second squared. Certainly that looks like an acceleration, but then again it isn't. Okay? First of all, this is the effect of gravity, right? What's gravity? Gravity is a force. The force of gravity acting on this object, since it's a force, it appears in the free body diagram, not the mass acceleration diagram. Free body diagram. So that g thing, that appears over here. Not the acceleration diagram, mass acceleration diagram, but free body diagram. This is a force. What goes into the mass acceleration diagram? Remember what acceleration is. Acceleration is just a time derivative of velocity. And velocity itself is just a time derivative of position. So this thing has a position. This block has a position, right? It's some distance down the slope. And then if I take its derivative, there's velocity, right? Which is some vector pointed in the direction of motion. And take the derivative of that thing, that's the acceleration. There's only one acceleration. So when I draw this acceleration diagram, it's really just one acceleration vector. It might have multiple components to it, but it's just one acceleration. The gravity is a force. Acceleration is just this sort of kinematic relationship. So in a moment, what I'm going to do is I'm going to take the free body diagram, mass acceleration diagram, pull off the vectors in the acceleration, and construct a set of equations with Newton's second law, equations that I can solve. In order to do that, I have to turn these vectors, right? The vectors, and F equals ma is a vector equation. To turn them into scalar equations that I can solve, I'm going to have to split them into components. So in this particular case, I'm going to choose components that are aligned with the ramp. So in particular, I'm going to choose a vector that way and a vector that way. So this one is tangent to the ramp. This one's perpendicular to the ramp. The one that's tangent to the ramp, I'm going to call direction E hat 1. The direction perpendicular to the ramp, I'm going to call E hat 2. So if I do that, then let's write these vectors here in terms of E hat 1 and E hat 2. The normal force, that one's really easy. That one's in the direction perpendicular to the ramp. That normal force is all in the E hat 2. So I'm going to call this N E hat 2. Right? N is a scalar. N is the component of this vector in the E hat 2 direction. Similarly, the friction is quite simple. So the friction force is tangent to the ramp. The friction force is opposing the relative motion, the sliding between these two surfaces. Since the ramp is stationary and the block is sliding down, that friction force, that sliding friction, has to be pulling upward. So I'm going to set this friction force to be F in the minus E hat 1 direction, since it's pointing upward and tangent to the slope. And then finally, this weight is straight down, right? And it's not so convenient with the E hat 1 and E hat 2, but we should know how to decompose vectors into components by now, so we should be able to do it. So it's an m times g sine of theta in the E hat 1 minus mg cosine theta in the E hat 2. Right, the magnitude of this force vector is m times g, and again, I'm just splitting it up into these fractions in the E hat 1 and E hat 2 directions. And of course, theta is this angle up here. So there's my weight, my friction force, my normal force, all in these E hat 1 and E hat 2 directions. Now, the acceleration is quite easy. In fact, this is the whole reason why we chose vectors that are sort of parallel and perpendicular to the ramp, because of this acceleration term here. Because that acceleration, as I said before, it's all in the direction tangent to the path, and that direction tangent to the path is a direction that's sort of parallel to the ramp. So therefore, this mass times acceleration is just ma times, it's in the E hat 1 direction. Notice I took the little squiggle off the a because my a now is representing this component, or the magnitude of that acceleration in the E hat 1 direction. So that's it. There are my vectors on my two diagrams decomposed in these directions that are going to be relevant for me. Now, before we move on, I'd like to make a little comment about this friction force here. So it's my little note here. So this friction force, F, I just drawn it in here, but for part of the time there is no friction force, right? So I'll say F is 0 for time less than TF, right? So before we get to this friction part, the friction force is 0. Does that make sense? So we'll leave that out of the equations when time is less than TF. But when time is bigger, I guess, or equal to TF, so after time TF, we're going to let F be, remember this is a sliding friction right here. And when we have sliding friction, sometimes it's called kinetic friction, the friction force is mu k times that normal, right? I should say that N, which is the magnitude of the normal force right here. This is the force by which the block and the ramp are sort of squeezed together. So friction force mu k times N. Again, that's a Coulomb law of friction. And then we'll use that when time is bigger than TF. All right, so we'll have two sets of equations, one for time less than TF, another set when time is bigger than TF, and we'll substitute these two different expressions for the friction in those two different cases. All right, let's make some more progress. Let me scroll this up so we have room to write. The next step is I'm going to construct some equations. And before I construct equations, one of the things on my problem-solving checklist is to explicitly state the physical principle that we're using. And as I said before, we're going to just be using Newton's second law. And sometimes when I write this, I just write Newton. It's just the second law is implied as a physical principle to use when solving a problem. But this essentially says, of course, that the sum of all the forces equals mass times the acceleration. Of course, this is why we constructed the free body diagram and the mass acceleration diagram to begin with. But there it is. And of course, Newton's second law is a vector equation, right? It's got a sum of force vectors. And it's got a mass times acceleration vector. And what we're going to want is some scalar equations that we can actually solve for things. So what I'm going to do is take Newton's second law here and split it into components. I'll look at the E hat 1 component and the E hat 2 component. Like so. So the E hat 1 component, what do I have? I just look off my free body diagram, mass acceleration diagram, pull off things in the E hat 1 direction. So for example, I have this component of the weight, which is mg sine theta, that's the weight pushing down the ramp in the E hat 1 direction, or a component of it. And then I have the friction, right? That's also in the E hat 1 direction. And of course, the friction is only active when t is bigger than tf, but I'm just going to write it here. And what's that equal? It's equal to, those are all my forces in the E hat 1 direction, or my forces with components in the E hat 1 direction. And then I go to the mass acceleration diagram, all my accelerations in the E hat 1 direction. So I've got m times a. And that's my equation for the E hat 1 direction. Now, of course, I also have an equation in the E hat 2 direction, right? This is the direction perpendicular. Here I have an m times g cosine theta, right? That's my component of the weight. Actually, it's a minus mg cosine theta. I got to be careful with that. And I also have a normal force, right? And those are my components of the weight in the E hat 2 direction, or components of the force in the E hat 2 forces in the E hat 2 direction. And I've got to set that equal to the component of mass times acceleration in the E hat 2 direction. So what do I put there? Give you a second to think about it. What goes there? Well, there is no acceleration in the E hat 2 direction. So what goes here is a big fat 0. And there we go. I've got equations number 1 and number 2 that characterize the dynamics of my problem. These are the equations of motion, if you will. So I have these two equations of motion. Now, what am I going to do with them? Well, I could, and I say could, I can take this first equation and solve it for the acceleration. So this would be A equals g sine theta minus F over m, right? So friction force divided by mass, assuming there is a friction force. For part of this time, there is no friction force. But that would be the acceleration. And F, when we do have friction, F is mu kn. And the second equation tells me what n is. That's kind of nice. So n is going to be equal to mg cosine theta. And this is kind of interesting, I think. And to see why it's interesting, let's go back and think about it the way we did when we were doing analysis without equations, when we were sketching graphs, right, rather than solving equations. So here I can solve for acceleration. Acceleration is just going to be g sine theta in the first part when there's no friction, right? Friction will be gone. And then when we have friction, I can make the substitution and put this other piece in there too. So let's do a little bit of plotting just to see where we're going with this thing. So the first thing I'm going to do is plot the acceleration as a function of time, right? We did this before. I'll put a TF right here. When time is less than TF, what do I get? This first equation up here tells me that that A is equal to just G sine theta, right? G is a constant, theta is a constant, right? The ramp isn't changing its slope. So this is just some positive constant. G is 9.81 meters per second squared. Theta is, what, 20 degrees or something like that. So for this first part, acceleration is constant and positive. So it looks something like this. And then when T is bigger than TF, or bigger than or equal to TF, what do we got? We got A equals G sine theta again. But then I have to add in my friction part as well. So I got minus F divided by M. F is mu K times N. So it's mu K times M times G times cosine theta, but I'm dividing by M, so that M's going to cancel that one, so it's going to be mu Kg cosine theta. I'm hoping that fed on the screen right there. So there's this one. And, what is this? Again, it's constant, right? G, theta, mu K, G and theta, those are all constants right there. So acceleration is a constant again. Is it a positive constant or is it a negative constant? Well, let's think about this. For this first part, if I were to plot on the second plot the component of velocity as a function of time, then velocity, remember my thing starts off with zero speed, so it has to start off there. And since acceleration is positive and constant, that velocity must be increasing linearly like so, right? So it's speeding up as it's cruising down the track. And then when it hits the friction, what's going to happen? Well, if the acceleration remains positive, that means what? The velocity is going to just keep on increasing, right? But I told you that the block comes to a stop. So therefore, what has to happen is this block has to slow down, which means the acceleration has to be negative in order to bring the speed down. Okay, so the acceleration is negative, the acceleration is constant, so therefore the second part of this acceleration plot has to look, I don't know, something like that, which means the velocity should go something like that. So this is what I get from those accelerations. Now what we're interested in, do you remember what we're interested in? Let's go back up here. Got to keep it in focus here. What we want to find is the time at which this thing stops. We want to find this TS right there. So what's the time at which it stops? Well, we have to find the time at which this velocity goes back and hits zero again. This is what we want, the TS right there. Aha. So now that's the big picture, right? There's the big picture. That's what we want to be able to calculate. We've got the acceleration. We've got explicit expressions for those accelerations. We should be able to integrate them to get expressions for velocity. And we should be able to find the time at which that velocity goes to zero. The time TS at which velocity goes to zero. That's our roadmap of how we're going to finish this problem. So with that in mind, let's go ahead and do these calculations. I have acceleration. I'm going to have to get velocity, right? That's going to tell me where this thing stops. So I'm going to start off in this first interval right here before we get to TF. So between 0 and TF, the speed is just the integral of the acceleration. The acceleration is g times sine of theta. And I'm integrating with respect to t. What's that, right? The integral of sine is minus cosine, is that right? Be careful. I'm not integrating with respect to theta, I'm integrating with respect to t. There is no t in here, right? A is just a constant. A is just a constant for this first interval. So this integral is quite simple. It's just g times sine of theta times t. And then I also have a constant of integration. I'm going to call it C0, right? V equals g sine theta times t plus C0. And what I need to do is find that C0. How am I going to do that? Well, the way I find those constants of integration is I go to my initial condition. My initial condition says at time equals 0 that the V has to be what? I start off at rest, so V at time equals 0 has to be 0. Well, if I stick t equals 0 into this expression, I get 0 plus C0, right? Since t equals 0, I'm multiplying this whole thing by 0. It gets rid of that completely and left just with the C0. So C0 has to be 0. So C0 gone. And therefore v is just g sine theta times t. Just like so. Now, where am I going to go with this further? I'm going to have to solve for this one too. So I'm going to need to know what v is at times tf. If you don't see y yet, y right now, you're going to see it in a second. So let's just do a little bit of further stuff. So let's say look at v at tf. Here's v as a function of time. V at tf, I just substitute tf in there. So g sine theta times tf. Tf is something known, right? Tf is one of these things that has been given to us. So here's an expression for v during this first interval of time, and there's the value of v. This in green here. There's the value of v at this time tf. So there's the value of v right there. All right. So now what I have to do is find an expression for this, for my velocity for this interval of time. So let's do that as well. I'm going to try to sort of squeeze that in. We're over here. So let me just write this in. So here I'm going to look at t between tf and ts. So in this interval right there. So when we've got that, then we have v, which is the integral of the acceleration. But this time the acceleration has both these pieces in there. And I'm going to notice that both of them have a g in there, so I'm going to actually pull that out. So we're integrating g times sine theta minus mu k cosine theta. And we're integrating with respect to time, right? So when I do that again, all this stuff, my integrand is all just a constant. So this is g times all this stuff right there, that all goes inside there, times t, again, plus another constant of integration. I'm going to call that c1. Now how am I going to find that constant of integration? Looks like it's a creep up there. So what I'm going to do is I'm going to take v, this is my expression v, but I'm going to evaluate it at this tf, the time at which the friction starts, right? And here I'm checking a boundary condition, so I'll abbreviate with that with bc. So v evaluated at tf, I got g times all this stuff in the parentheses, and I'm going to write it out this time. So there's the stuff in parentheses. And I'm evaluating this at t equals tf, so I'll evaluate this, put tf right there. Then plus that constant of integration, c1, and this has to equal the velocity of the box at tf coming from the left side, right? Coming from just before tf. And that's this expression right there. So this has to equal g sine theta times tf. And you'll notice something quite nice here. On the left-hand side, I've got a g times sine theta times a tf. On the right-hand side, I've got a g sine theta tf. That's supposed to be a tf, by the way, right there. And so therefore this term exactly cancels out that term, g sine theta tf, right there. And that tells us that c1 has to be, where is it? G times mu k cosine theta tf. Huh. Don't forget the tf. So therefore, where are we? So here I have, where it is, right here is an expression for velocity as a function of time. I'm going to put this value for c1 in there, so maybe I'll just write that out right now. So I've got g sine theta minus mu k cosine theta, that's the stuff that goes in there, times t, plus c1, c1 was this piece right here, plus g mu k cosine theta tf. Whew, so there's a pretty long expression for my speed as a function of time. Remember, this is just for t between tf and that end time, ts, that stopping time. So it's only good for that. In other words, it's only good for this second interval right there. And then, what do I got? So here it is, and where am I going again? I want to find, what do I want to find? This is why we write it up here. I want to find that stopping time, the time this block comes to the stop. The time the block comes to a stop is right there. The time the block comes to a stop is when this velocity goes to 0. And what is this velocity? Well, I've got a mathematical expression for that velocity. Here it is. I need to find the time, here's time, at which this expression goes to 0. In other words, what I want to do is I want to find Ts such that v evaluated at Ts equals 0. And that's pretty simple to do. I set this thing equal to 0, solve for t, and that's it. So I get Ts is equal to the following. When I do so, I get a minus g mu k cosine theta tf at the top, right? That's that piece right there, and dividing by this piece. I can simplify this just a little bit. Notice that I have a g right up here in the numerator, another g right there in the numerator. Those two can obviously cancel out, so I can just get rid of that and get rid of that. And what I do with an answer is I put a box around it. That's another part of my problem-solving process. When you have an answer, you're happy with it, put a box around it. There's my answer. Now, before we actually settle on this answer, what I'd like to do is make sure that this thing makes sense. Does it make sense? To check if it makes sense, one thing you can do is look at the units of this thing. Everything in mechanics has units of mass, length, or time, or some combination of those three, okay? So what are the units of this quantity right here that I've got? So first of all, I've got mu k, what is that? Well, if you think about mu k, where does that come from? It comes from the friction force. We said that the friction force is equal to mu k times a normal force. Notice that the friction force has units of force, right? This is a mass length over time squared, so that's a force. And the normal force, that also has units of force. So if I have a force here on the left, I also must have a force here on the right. So in order for this thing on the right to have units of force, this mu k has to be unitless. Can't have any units. So this thing's unitless. So mu k unitless. Cosine theta, what are the units of cosine theta? Well, again, think about what cosine theta is. Let me just draw a little triangle here. Cosine, let's suppose this angle right here is theta. Then the cosine of theta is just this. Oops, not that one. How about this one? That angle right there, the length of that side divided by the length of that side. The adjacent side divided by the hypotenuse. It's a length divided by a length. So therefore, cosine theta is also unitless. Well, that's kind of boring so far. And notice that sine theta, for the same reason, it's the opposite side divided by the hypotenuse. That one's unitless. Mu k is unitless. Cosine theta is unitless. So everything in this expression on the right-hand side is unitless, except for the time. The time has units of time. So what we have here is on the right-hand side, we've got something that's unitless divided by something that's unitless times something that has units of time, and we're expecting to have something in units of time, so that checks out. That's kind of cool. Another thing you can do is to check whether this expression makes sense is to think about what you're expecting for this time, right? Remember this whole experiment started at time equals 0, right? The thing was released at time equals 0, it picked up speed, then time equals tf, it hit the friction, and then we stopped at time equals ts. Well, this expression we get for ts better be bigger than 0, right? It started at 0. It better be stopping in the future, not in the past. So let's look at this thing, make sure it's positive. Uh-oh, that minus sign is probably a little bit worrisome, right? That minus sign might be making everything negative. So let's look at that. So in the numerator, I have a minus here, mu k. Mu k is positive. Cosine theta. What's theta? Theta looks pretty modest to me, like maybe about 25, 30 degrees, somewhere around there. So cosine of theta, cosine of 25, 30 degrees, that's something positive. TF is something positive, so the numerator is positive except for that minus sign. That's not good. Let's look at the denominator. I got sine theta minus mu k cosine theta. Is that positive or negative? Well, let's recall. Let's look at my expression. Remember, here was my expression. G times sine theta mu k cosine theta. G itself is positive, but I have this expression sine theta minus mu k cosine theta in there. Remember, mu k and theta must be such that the acceleration is negative right here. Otherwise, the thing would never come to a stop. So therefore, sine theta minus mu k cosine theta, that has to be negative. This term in the denominator has to be negative. So I got something negative in the numerator, something negative in the denominator. So therefore, the thing that I get in the end is positive, and that's exactly what I want. And that kind of, at least, checks out. I'll say it that way. By the way, I went through this a few times. I'm pretty confident about this answer, so I'm going to stick with it. There's my answer. I've got it boxed, and the problem is done. Woo!